Hello everyone, I am Harshit Tiwari and I am here to take you through the entire technical architecture of our solution towards the problem statement number 7 of Bharat Antariksh Hackathon. Now, before taking you through the code base, let me take you through the architecture and this entire uh, thing. So we are using Flutter as a front-end framework along with the material design for the UI part to maintain a proper balance between the UI as well as performance so that the app performs really smooth and really well on low-end devices as well. We are using Flutter for two main reasons. The very first is for having a robust and single code base and catering towards multiple platforms. The second reason is for the security and the lightweight nature of Flutter. Now, for the data services part, we are using Pexels API for showing a visual representation of how a city looks like, and we are using multiple APIs of Google Cloud Platform, which is Places API for having a proper searching functionality for places, so that the user doesn't have to use coordinates for searching for any location. And then we are also using Google Cloud SDK's map platform for having our heat map functionality. Now, for the offline and storing the cache, we are using SQLite so that this entire app stores everything locally once the data is being transferred from the server to the Flutter app. Now, before understanding the backend and this entire machine learning part, I need you all to understand the data sources. Currently, we are using ISRO's EOS 6 Stack satellites data and CPCB's API, which is Control Pollution Central Pollution Control Board, for having cities and more data like NO2, SO2, and CO. And we are also using IMD's API weather for accessing more than 3000 stations and getting the temperature and rain data. So this was the entire like data part of how we are fetching it. Now this won't be manual. It is completely automatic. All we just need to do is like set up our authentication like ways, and then everything would be done by the pipeline, which I will be explaining later. Now, for now, we are using Superbase as our database, which is something we are migrating from because Superbase is having a lot of limitations, and it is not letting us have a proper and smooth coordination between the backend and the database. So our team is constantly working on migrating the Superbase to some other cloud provider. Preferably, we are using Azure or Google Cloud Platform as our custom database. And then we have cloud services and API. Now, for the notification part, we are using Firebase cloud messaging as we will be like writing up custom logic onto that logic. The user or the people of specific area, if we're facing some sort of issues, they would be receiving a notification as well as a health advisory. Now, this threshold is like just for representation for now. We are having some like more complex logic where this entire each and every part aspect of this entire CPCP API would be used. Now, for the mapping and visualization, as I told you earlier, we are using Google Maps API for interactive heat map, and we are also using Places API for naming the locations. And then we are using Pexels as I told you earlier. Now, coming to the main part, which is the core of this entire app, which is the backend part and this entire automatic nature of this thing. Now, for the backend, we are keeping it very simple and straightforward so that the entire process is seamless and smooth and does not take much time in having everything. So the user would be like giving their location in terms of sharing the current location, or they can give a name of some location. Initially we decided to keep it coordinate wise, but now we are sticking to like having a proper naming convention for each and every place. Now, on to receiving the location, the server would fetch the coordinates and the name, and it would fetch the data from the backend and process everything on the server. Now there is a calibration API set up on the server which would calibrate the ISRO's captured data into particulate matter 2.5, which is the standard convention for keeping the data and readable by humans. Now, for the machine learning part and the calibration part, we are using a gradient booster regressor, and we are like having satellites AOD data, minimum temperature, maximum temperature, rainfall, days of the week as our input feature, and it is like returning us the ground PM 2.5 value. We are also using like standard scale and normalizer for normalizing this entire thing, and we also perform some sort of feature engineering so that we can cater like diverse areas with multiple features which affect this entire air quality. Let's take an example. If we are like targeting Uttarakhand, there are a lot of factors which affect AQI over there, as the satellite would be just capturing the ground level data, and the feature engineering layer would enable us to capture those patterns of those specific areas and training the entire calibration model in such a way that it returns the accurate particulate matter 2.5 data. In terms of endpoints, here are the major endpoints which we listed, although we added two more endpoints, which is for the heat map and for the forecast. Now here we just have the real-time AQI, and then we have forecast, and then historical location and timestamps. This is for a time series trend analysis, which I will be covering in the later aspects of the video. But yeah, this is the like very simple and very straightforward architecture. Now coming to the main part, which is the forecasting thing, we are using a hybrid model which consists of LSTM and ARIMA. ARIMA is for linear prediction and linear dataset, whereas LSTM is to like recognize non-linear dataset, non-linear patterns, and according to that we are using dung beetle optimizer to optimize the weights accordingly and can have a proper forecast catered towards specific areas, not just specific areas. This entire feature engineering would be like taking care of this forecast as well. Now talking about the code base, this is the very simple and very straightforward code base. Here we have four major components, which is the calibration API, the API which is the like Node.js backend, as well as we have this processing directory which is having all the models, all the content of this calibration API. Now to make sure everything like is properly aligned, so our main thing is this lib folder, which is the entry point of our Flutter app. Now in our Flutter app we are like giving the asking the user to either give their location in terms of coordinates or place, or he or she can share his or her location through their GPS coordinates. Okay, now after fetching this, we are sending it to the API directory. Here this entire entry point, and here we had to make sure that we are separating the heat map as well as AQI, because the heat map part was taking quite long for us to process it on the backend, so it was kind of slowing down this entire progress. So we separated this thing AQI into two parts. First is that the server would return the AQI, and on to receiving the AQI, the server would send heat map, so that the Flutter app handles the state management really well and does not crashes onto onto having low area networks. Now for the calibration API, the moment we receive the location from the Flutter app, it would be like sent to the index.js, where it would route to the AQI and the heat map. Now what AQI would be doing is asking the Superbase database to return the values of what we are having. For instance, we would be receiving the AOD data and the ground data, and we would be receiving the temperature, rainfall and everything. On to receiving everything, this thing would be calibrated with the help of calibration API. Now calibration API is basically a simple Flask app which is utilizing all the models which we are having over here. in the processing directory. Now, the processing directory is the main key point, main entire core module of this entire app. As here we have three major models, which is advanced feature engineering, and then we have ensemble model. So what ensemble model is doing is that it is establishing a communication between the advanced feature engineering and this train calibrator. Now train calibrator is basic a simple basic gradient booster regressor model using utilizing standard scaler to scale this entire data set and feature scaling. We also try to diversify the data set so that this entire thing does not overfits or underfits, and we also utilized dbu as I mentioned earlier, so that this entire thing does not overfits. Now in the advanced feature engineering, we are making sure that we are capturing all the temporal patterns, which is seasonal cycle, latitude, longitude, and AOD rainfall and AOD temperature. This thing is for those areas where the AQI is directly affected by the area it is. Now that's what I told you earlier, that this entire feature engineering part is the core of this app, as it is making sure that the AQI is not just calibrated, but it is also fine-tuned in such a way that areas whose AQI depends on to the several factors, those factors are considered over here. Now coming to the main part, which is the forecasting, we are utilizing some of the main research papers which suggest us to use a hybrid model, and onto using that hybrid model we are able to forecast it. Now let me show you the current progress of this Flutter app. So here I have started the calibration server, and here I have my API server, and then we have this thing, Flutter app. So I'll just simply run this Flutter app, and it would I would choose iPhone 16 Pro for instance. Now on to choosing iPhone 16 Pro, it would launch it in my iPhone. Now as I told you earlier that we are catering towards multiple platforms, which is iPhone as well as an Android. So the app is currently working flawlessly on both platforms, including iOS and Android. Let it build. Now as we can see that our app is compiled and signed, and now we have our app usable in a usable format. So now this is how the app looks like. Everything is initiated. Now we can either use manual location and search for some location. For instance, I can search for Varanasi and I will be getting the suggestions, or I can just simply go for the current location. So I'll just use my current location, and it will do use my current location, and see I have Raebareli here. So the AQI is 48, and it is showing the forecast. Now we are constantly working and enhancing this entire forecasting, and as well as showing the day wise forecast of this entire AQI. Here we have location wise map of this entire thing, and it is showing the temperature and the rainfall. Now here, since we are using an iPhone simulator, it is limited by the Apple, so we are just getting this button overflow, but it is not there in our main app when we are using it on iPad or iPhone or Android. Now talking about the heat map, we have this thing over here. You can see it does show the map and fetches our current location, although the heat map functionality is still under development. We would be pushing it as soon as we are done with it. In the profile section, we have our location of all the cities and all the cities and the AQIs we fetched. We can also add one of them in our favorites, and this is how our thing would be working. Now everything would be saved onto a local SQLite database, which is here on our app. For example, if I close this thing, it would cache the location as well as it would cache the data. For instance, if I just cut short this thing and use it again, it would fetch from the cache and it would show. Now, on the basis of these things, dummy data has been shown, and it would like continue to show it as long as the data is valid and not refreshed. So this was the like entire architecture and everything. Our entire code base is hosted over on GitHub, and we have our database over here, and we have our GitHub as well. So I hope everything is like really simple and clear. For more queries, you might comment it down. I will cover it in the next video. Thank you so much.